Hello, everyone, and welcome to this webinar where we will be featuring our new turbidity sensor. I'm joined here today by my colleague Reidun, who is running the webinar. And we're very excited today also to be have Anders in Sweden and myself here, Inger Graves, in Bergen. We hope you're having a good day out there. It's in the afternoon here in Bergen and starting to get dark already. But what you'll be seeing here is hopefully going to lighten up your day. So before we start and look at the sensor itself, Anders and I will introduce each other. So I will introduce to you Mr. Dr. Anders Tengberg, who has been my colleague for many years. And he's an application specialist and water quality product manager here at Aanderaa. He has been key in the development of the oxygen octode, and he is managing all the various sensor projects to improve our ocean and coastal observations. His key interest is to really understand the complex nature around us with trustworthy technology. And besides working here at Aanderaa, he also has a part-time position with the Chalmers University of Technology in Sweden. Anders, why don't you...
Yes, thank you, Inger. And hello, everybody, and welcome to this webinar. So Inger is the lead of our ocean and coastal segment for the whole Xylem operations. And she has been with the company since 2003. And before that, she used to work in Portland, Oregon, in the United States for Intel, development of microprocessor. She's always enthusiastic about new things and about the things that we develop and about new projects. So I hope, you will join the webinar, enjoy the webinar today. Thank you.
Yeah, so Reidun is reminding me that as we go along here, you will of course not be able to talk or we will not hear you, but we would love for you to note your questions and send them in via the chat function, and we will go through it at the end of the webinar. So let's move into the materials, and just sort of as an introduction here, remind you about our single sensor solutions, our family of sensors. That you see here to the right, where we have oxygen pressure sensor, which also measure wave and tide, turbidity sensor, temperature, salinity, and currents, along with waves, also motion-based waves. For all of our sensors, we take great pride in our multi-point calibrations. And for those of you who watched the live launch for our turbidity sensor, you got a little bit of a look into our labs there. We want our sensors to be open and easy to integrate both to loggers, whatever logger you're using, to data, to maybe to a computer just directly, or to any back system that you may have. And this is also the same for the new sensor, turbidity sensor. Low power and different depth ratings is common in our sensor portfolio also. And so we really take pride in our accuracy and robustness and long-term stability. So this is an overview for the sensor portfolio, and then Anders will talk a little bit about and give an intro to turbidity and water quality in general before we dive into the sensor specifics.
Yes, thank you, Inger. So this is about turbidity. What is turbidity? And it's just a measure of water clarity. So it describes the light which is reflected against particles in the water. And you can see that to the picture upper right. You send out light, which is in 880 nanometer range, and then it's reflected against particles, and the reflection against particles gives you a measure of turbidity. As many other parameters, optical parameters like chlorophyll or CDOM and other types of optical parameters, turbidity is not an absolute measurement. If you want to have absolute amounts of particles in milligrams per liter, for example, you need to take water samples and correlate to your turbidity measures, because they can vary from site to site. But we will get back to that during the presentation. So Then turbidity units, there are 3 different units, FTU, NTU, FNU, which are basically the same. NTU was the first American standard, nephelometric turbidity units. FTU, Formacin turbidity units, and then FNU is the European standard. But basically, you can put you can say that they are equal. So I think this is what, of course, if you have higher levels of turbidity, this is bad for biology in the water. And you can see here on the lower graph how different levels of turbidity, how they influence biological processes in the water. So we did this. I think we moved to some of the applications.
Yeah, and we would like to break down really the our coverage of the sensor in sort of 3 main topics, I would say. One is around the versatility of the sensor, which is surrounding the how it can be used in various different applications and why it's specifically suited for that. We're also going to have cover a little bit about how it relates to the oxygen optode backbone. And then also Anders will show us some interesting data and look at how we can use turbidity sensor along with acoustic sensor, sending basically acoustic waves through the water column. So first, if we go to the versatility, why it's so versatile, why don't you talk a little bit about the aquaculture market, Anders?
Yes, sure. So yeah, in aquaculture, it is an important parameter, maybe not the most important one, but useful, for example, to see how much particles there is in the water, which can be related to feed of fish or input of particles from another source, but and also very useful in relation to more important parameters like oxygen, currents, and in some cases salinity as well. Then where turbidity is really important is in dredging, isn't that so, Inger?
Yes, and we worked over the years with dredgers with many different parameters, and in dredging, obviously monitoring the suspension of the sediments while you're doing the dredging activity, making sure it doesn't become too high. And also then cause situations where you have life-threatening situations for the systems, the ecosystems surrounding the site is of course of vital importance, where they use these sensors to give very rapid updates on the status around the site. And it's in the up-and-coming marine minerals industry, it's sort of a similar problem, right, Anders?
Yeah, and in marine minerals, of course, yes, when you extract marine minerals, in many cases, you will create resuspension of sediments, which can be contaminated and which can also contaminate the ecosystem because you spread a lot of particles. Of course, in shallow waters, this is well known, and but now there is a big push to move towards deeper waters. For example, trying to extract manganese nodules in the deep sea, and that will, without any doubt, need to be surveyed if you don't want to have a really serious impact on the marine benthic ecosystems at these great depths. Then about coastal erosions, we will come to that in a slide. We also presented that during the live launch webinar.
Yeah, and also we'll look a little bit more at the effects of trawling. So really, all these applications, it's really surrounding how do you measure the suspension of minerals, the turbidity that's affecting the marine life around the site, and also to look at in some of these cases about the erosion of the coastline. So let's go into a little bit more of what is Anders's primary interest these days, which is calibrations and accuracies and making sure that we have a field accuracy of the steps that we have in our data sheet. So Anders, why don't you say a little bit about our calibrations for the turbidity sensor?
Yes, so as with all our sensors, we try to, we multi-point calibrate them. we don't leave calibrations to customers. We estimate that we can do it better in the lab when you have controlled conditions. And here we see how these sensors are examples of how these sensors are calibrated in the lab. In the upper graph, you see the relation between the FTU, turbidity units, and the raw data response of this sensor. And then every sensor, before it goes, after calibration, before it goes into the field, we verify how well it performs with respect to the specifications that we give, and that you see in the lower graph. And normally our sensors are very well within the limits of the specifications we give, because when you go to the field, typically you lose some of the accuracies. So we want to be very well within specifications, as you can see in these lower graphs. This does not only apply to turbidity, it also applies to all the other sensors that we do multi-point calibrations on. So yes, I think at this time sensors are delivered in in 4 different ranges, which you can see at the bottom point here. And we have a 3% absolute accuracy in the selected range.
So I think also, and now we're going to get to a very crowded slide here, probably breaking all the PowerPoint rules in the world, but we wanted to show a little bit to you, the writer is nodding. I wanted to show to you a little bit about how you get from the measurements that we produce from the sensors to the total suspended solids. And Anders, why don't you say a little bit about that?
Yeah, so what you really normally are looking for is how many grams or milligrams per liter of suspended solids you have in the water. That's normally what the authorities gives you as a limit, and that's normally what you're interested in if you want to look at sediment resuspension and sediment transport, how much sediment is resuspended. So when you work in a site, and if you want this to be fairly accurate, then you need to take water samples, you filter them, you dry the filter, and you weigh the filter before you filter the water on it and after, and then you get your values in milligrams per liter. And here on the left hand side, you see how this is a sheet, an Excel sheet that we supply with the sensor. And that gives you the possibility of putting in your calibration values, and then after that entering these calibration values into the sensor. So if you continue to work at a specific site, where then you can just copy these coefficients, which you see at the bottom here in the gray box, and send them to the sensor. And then the sensor will also give you the total suspended solids, TSS. This is also something that our sister company YSI is doing. So we are doing it in quite a similar way, converting from field data and putting that into the sensor.
And we snuck in the slide after marketing had actually looked at our slide deck, so this is why it looks like this. But this tool makes it possible to get these types of TSS measurements out of the sensor. So let's see a little bit more about the field measurement. And this was the example where we had in our live launch, we had stationed Anders out there on the close to the Swedish coast, or on the Swedish coast. He was looking at some erosion studies that he's been doing there with using the new turbidity sensors instead. While filming this, a Swedish swimmer came by, so that was quite interesting for Anders. And fortunately,
a swimmer, but not naked though.
Not naked. Well, that's a good thing. So,
but
anyways,
I managed to redirect them to another exit.
But why don't you say a little bit about the instrument you used and the data that you collected on a similar occasion there?
Yeah, these are studies in shallow coastal studies along beaches to look at erosion and buildup of beaches. You know, a sandy beach can disappear in just in one winter storm, and it can be built up in another one. So understanding this process is important if you want to give coastal protection and yeah, how to protect your coastline. And in this case, we use a Seaguard instrument, and here the multi-parameter feature is very useful. We measure currents with a single point current sensor. That's the orange one. This is an old instrument, so it has orange. The new ones has black. And then we include the wave and tide sensor, which is pressure based, and it gives us all the wave information we want to. It doesn't give the directional wave, but it gives us all the other wave parameters. Salinity is useful to look at input from nearby rivers and how that mixes in, and if it's river water that transports in particles, for example. Then we have the oxygen, which gives us biological information. You know, these sandy porous sediments, they act as bioreactors, and here a lot of the organic material is recycled, and during daytime, when there is light and nutrients, you have high supersaturation of oxygen, and during nighttime, low levels of oxygen. And then the most important feature here is the dual turbidity sensors, which you see one above the other, and that gives us possibilities to see how much of the sediments are resuspended by waves and currents, and how they are transported in different directions. Why 2? Because with 2 you get the gradient, and then you can roughly calculate, if you have resuspension of the bottom sediments, approximately how much is resuspended. And typically in these studies we bury the instrument to what you see here, the yellow line. We bury them in the sand, and then we have a long line to something where we can, so that we can find the instrument in case it gets sanded over, for example.
And it could be quite thrown around out there, so it's good to have very solid construction, I guess. So here's the data. I want to say a couple of things about that, Anders.
Yeah, this is just a short test deployment, so just a couple of hours. What you see on the upper graph in red and blue is turbidity. Red is turbidity which is placed higher up, so further away from the bottom, and blue is turbidity closer to the bottom. And they should be read on the left-hand scale there. And yes, you can see turbidity closer to the bottom is higher and more variable. You have small resuspensions of sediments here. Although it was very low levels of turbidity during that day, it was quite a calm sea, no waves, very low currents. As you can see on the lower graph here, where green is current speed, never above something like 10 centimeters per second, and waves very small. They are on the purple graph and should be read on the right-hand side. And but we have one occasion with some waves, and that's from a ship passing further out in the strait. So it's very useful to see here how we have these occasional waves coming in, and if from ships, for example, and if they can really play a role in resuspending sediments and in coastal erosion. On the top picture, you see currents that we measured, and the arrows, they give you the current direction. So in this case, the currents were parallel to the coast, as they often are, and going towards the west. So yes, I think this was in brief about.
Yeah, I think you could be talking about this for a long time, but we try to keep within our time frame here, and so we want to talk a little bit about the relationship with this sensor and the oxygen optode in terms of the backbone and what we've learned from our experiences with the oxygen sensor. And obviously this sensor has been very successful. It's been in many scientific studies, and has become really a baseline for oxygen measurements, particularly in the oceans, but also in coastal situations, in aquaculture and everywhere. And you know, one of the things that we really wanted to make sure we did with the turbidity sensor was these high-end optics, take some of the learnings with picking the right components and the right type of materials in the turbidity sensor as well, obviously due to it being an optical sensor. We constructed it so that it has ambient light rejection, which means that you don't get affected by changing light in the area. so that your turbidity measurements, being an optical measurement, you could imagine that could be affected by the changing light. And because of this calibration that we do with our sensor, if you replace the sensor with a new sensor when you're taking one in for maintenance or you're just changing things around, because it's calibrated completely, they will measure the same as, they will measure, their measurements will correlate and will be the same. So there'll be no jumps in the data, which you may experience when you're replacing sensors from vendors that don't do a complete calibration, where you do have to sort of adjust them in. We're using titanium, and we have a scratch-free sapphire glass, which is also a learning from working with similar types of designs in the Optode product family. So now we're going to move on to something that we find also very interesting, which is the combination of acoustics, which we do a lot of here at Aanderaa, and turbidity. And this is one of the reasons why we also wanted to push the turbidity sensor out, was that we wanted to have a good sensor for combining with acoustics with our CGAR2 family and provide additional value. So why don't you tell us a little bit more about what that value is, Anders?
Yeah, so I mean, with our instruments, as you saw in the previous example of coastal erosion studies, you could see we can put turbidity sensors at different levels, and that's a good prime interest, because you can then put turbidity sensors. Here was only a very little gradient, but you can put them on a string and higher up, and then you can combine acoustics with the turbidity measurements. So you can see if there is sediments resuspended from the bottom, that they come from the bottom, and how high up they spread, for example, clay particles, which typically bind to contaminants in the sediment and transport it. And you can then, for example, exclude on the acoustics. They pick up many things. If you will see in the next, you see on this slide, but also on the next one, they pick up zooplankton migration. They pick up biological primary production. Acoustics is very sensitive to bubbles, and you need to, but turbidity is not, and you can see that on the next slide here. Which is from trials in a pool, where you can see in red and blue, it's two turbidity sensors, which are for different ranges. One was for 0 to 500, the other one from 0 to 25. But you can see they show very low turbidity readings in this clear filtered pool water, about 0.1 NTU. But the acoustics is in black, and in this pool there is an electrochlorination system which creates small bubbles, and you will see whenever this is switched on, which it is around 8:24 or so, you see how the acoustic reflections jumps up and gives you much higher reflections. Basically, the reflections before, it's something like clear winter waters, minus 45 decibel, and then jumping up to something which is in summer water with a lot of production in the water. Then you have minus 10, minus 15 in coastal waters. So you see how much these air bubbles affect the acoustics, but there is absolutely no sign of in the turbidity. The turbidity does not see the bubbles. So combining acoustics and turbidity, and sometimes also with other parameters, gives you a much better certainty to which type of particles you have in the water, where they come from, how they are transported. And
I think that's really, and you also brought in this example of a project that you worked with in Sweden that we thought was a good illustration of how that can be used in practice. How does that actually play a role when you are doing your studies here? And this one with regards to trawling and resuspension, and a particular site where you really did not want resuspension to happen.
Yeah, absolutely. Yeah, this was at the site, 200 meters deep site, 200 meters of water depth. the west coast of Sweden, and it's a particular site because here chemical weapons were dumped after the Second World War, mainly mustard gas, and they were placed in ships, and the ships were sunk, and there is about 14 wrecks there full with chemical weapons, and because there are these wrecks, there is a structure on the bottom, and then there is more fish. So here there's a lot of trawling, and we wanted to see how trawlers resuspend sediments and how that the fine particles are transported, and if that leads to higher concentrations of toxic substances in the sediments because of this resuspension of sediment and sediment transport. So what you see, the peaks here in black, the black graph, that's measurement with a turbidity sensor placed on the instrument itself, and the instrument was about 2 meters above the bottom, and each of these peaks is related to a trawler passing at different distances from the instrument, and why we can say that it's a trawler, because we combine this with looking at AIS, automatic identification system, so we know the trawlers when they are passing, we can track them, and then we can combine by overlay plotting this turbidity on the acoustic backscatter, the reflections. You can see that reflections, the scale here is 0 to 50 meters. The turbidity is resuspended by trawlers, and it spreads higher up in the water column, and typically the particles that spread are clay particles, and clay particles bind more to contamination, for example, in the sediment. So we can see on the next slide what this leads to. If we look on the right-hand side, the map, this is a map of how much arsenic there is in the sediments, and this is a map created by the Swedish Geological Survey, and each of these dots represents a sample taken in the sediment and analyzed for arsenic. Arsenic exists naturally, but it was also part of the mustard gas, so there was high concentrations of arsenic in the mustard gas. In the red circle with the flag, you see the dump site, and the highest concentrations found in all Swedish waters was in the other red circle where you see it marked. And then we started to look into the currents in the lower 25 meters here, and that one you can see on the progressive vector diagram to the left. There you can see that the prevailing currents here are towards northwest, which is straight downstream from the dump sites. So we are quite sure that the trawling in this area is not a good idea, and we try to communicate this to authorities to get them to take measures so that trawlers could avoid these areas.
Interesting, and it also reminds us a little bit about marine minerals applications, where you're looking for the movement of the plume caused by the activities around the marine minerals, and I think the current measurements, can be used both as a way to see how much material is in the water column, but also, of course, to track what direction it's taking after having been suspended. So that's really interesting. So I think we wanted to then do a quick summary of what you've heard so far before we go on to some other interesting information. And so first of all, we went through to see what this turbidity sensor, how we can be so versatile with the sensor. And I think there's a couple of different aspects there. First of all, different depth ratings, different ranges, mostly also then the fact that it is completely calibrated for all of these different areas of use, and is back traceable to the sensor. The sensor produces a lot of metadata to enable you not only to know what it's measuring, but also which sensor is measuring it and what the conditions were. So I think that's something that is valuable when you are in the field measuring with several sensors. It's standalone, it's easy to use with both on-road equipment and other equipment in the back end. has open communication protocols, and can also then calculate total suspended solids. Why don't you say a little bit about how it relates to the oxygen optode backbone, Anders?
Yeah, of course. I mean, the optics and how you do the measurements here is quite different compared to the optodes, where you have a foil which is sensitive to oxygen. Here it's direct sending out light in the water, but the constructions are quite similar. It's in titanium and with sapphire glass, so that it can stand high pressure. And we see from previous experiences, for example, sensors which are molded, for example, at high pressure, the electronics can drift over time. But and then sapphire glass is also a good thing, because it's very difficult to scratch, and because also if you scratch a window on a sensor, and if it can be scratched, that can also appear as a drift, and then you must do something to fix that sensor. And yeah, we saw about the powerful combination with acoustic sensors, also combined with other sensors, gives you useful information. I think this multi-parameter is a very good feature if you want to better understand what's happening in the environments. And of course, as always, we try to make sensors which consumes very low power, because many of our customers deploy instruments for 1, 2, 3 years sometimes. So then you need systems which do not consume too much power.
So this sensor is only one out of many sensors in our portfolio, and over the years we've executed the sensor program for 2021. So why don't you say a little bit about what's happened with the rest of our portfolio?
Yeah, I mean, if we start from the left there, we see parts of 3 oxygen optodes. Now all the oxygen optodes are multi-point calibrated, 40-point calibrated. Even the shallow water aqua optodes will soon have that feature. On all the others, it's already implemented. To the lower left, we have an optode, which is our best-selling optode actually, but almost nobody knows about it, because it's used to integrate into cameras in aquaculture. And now we also start to offer that in other applications, and it's a useful sensor to integrate, I think, in many cases. It has temperature compensation just next to the foil. It's 40-point calibrated like the others, and it has 2 O-rings, so you kind of press it into the body where you want to mount it, and then it becomes flush mounted. Then we have the turbidity sensor that we talked about today, and I also want to point out, in the beginning of the year we released an improved version of our wave and tide sensor with improved algorithms. The previous ones we discovered were far too conservative, and with using these new algorithms we managed to detect centimeter waves from, for example, 40 meters depth, which was only possible from 10 to 20 meters depth before. So pushing the limits for how you can measure small waves with pressure-based measurements, and then combining that with the acoustic directional wave measurements with our, for example, CGAR2 instruments. And yes, I think, Inger, you have something to show here concerning the conductivity.
Yes, so we have a surprise for you today. There is something new coming that we're doing a soft launch of in this webinar as well. So you can't always control when things are ready coming out of the R&D department. We wanted to get this out as soon as possible. So here's a short video that will tell you about this new product.
What happened to the sounding? Or?
Unfortunately, no sound, Anders. So you'll just have to read it. So this is our new and improved conductivity sensor, the latest one in the sensor program from Aanderaa this year. And we're really proud to be able to finally get this sensor out and launched. It is a high accuracy connectivity sensor, and we call it the 5819, which is, we always have a number on our sensors. So why don't you tell us a little bit more about it, Anders?
Yes, so this one has much higher accuracy. Before we used to have we have the 4319 and
4319, you're right.
4319. Sorry, it's so revolutionary new number, so I got confused. But this one, we had two models there. One where the highest accuracy was 18 millisiemens per centimeter. This one has a factor of almost 5 better absolute accuracy. And we know from the previous version, from the 4319, that this type of sensor, this is based on our previous experience with that the drift is exceptionally low, also compared to other sensors, about 1 millisiemens, 1 microsiemens per month. And we also include here improved temperature response and an automatic change between low and high salinity. You know, different equations are used when you calculate salinity at low conductivities or at low salinities compared to when you are at higher salinities. Typically, the limit is around 10 PSU. This sensor, it automatically changes between low and high. That was also the case for the 4319. With the new one, we have calibration in more points, 208 points, and it's 6,000 meter rated. And then about integration, Inger, is that similar to before, to what we had before?
Yes, although it's just to reiterate, our ease of use really incorporates making it easy to integrate to whatever system you're using. You may have heard about ICAP, which is our proprietary, although quite open source interface that we use in our bus system internally. But we also want to make sure that anyone else can use it both over shorter distances with RS-232 and RS-422. So it's small, you know, it fits in the size palm of my hand, and it does not have a pump, which is a benefit to versus others that are using more complicated systems. Very low power, can therefore be up for a very long time on a very limited power package. So why don't we look a little bit at the sorry, wrong way. Why don't we look a little bit at some of the data we have for this and how it can be used, Anders, with the stability data.
Yeah, so the graph to the upper, the upper graph there, what you see is drift information. You don't see it so well there, but it's sensors, the older model 4319, which were coming in for recalibration at our facility. And we track them every time they come in and see how much they have drifted when they are recalibrated. And there you see the information, how we know that the drift of these types of sensors is very low. Yeah, so we track them. We have tracked them for over 10 years. Yeah, we talked about the usefulness of the CGuard 2. Inger, what you say about that? This sensor can be integrated.
Yes, so I think the CGuard 2 is a package that is one of the packages you can integrate this sensor with. And you know, again, what Anders has been saying previously, this combination of sensors to figure out you know, what's going on in the area of interest you're in, you know, mixing data from acoustics, from salinity sensors, from wave sensors, and now from the turbidity sensor, as well as the connectivity sensor that we now have higher accuracy. That combination there is something that we definitely see a lot of benefit of, and that our customers are using. So this is now making it possible to do even more high accuracy studies using the CGuard 2 platform that's already in existence. And then, of course, the CGuard can accept long strings, so you can string these sensors in the water column. And why don't you say a little bit about that? You use that a lot in Sweden, I know, Anders.
Yeah, and in several projects, we had an observatory, which you can see on the picture there on the lower left, with a string of sensors above. It was a short string, only 20 meters, but combining that, measuring oxygen, mainly oxygen salinity and turbidity at some levels, combining that with the acoustics, acoustic profiling gave us really useful information about ongoing processes in a fjord system. This was an observatory that we were running for 10 years. We took it up this year, and now we're using the string system in other applications, including looking at mixing from ships, for example. Then, for all our sensors, we try to have easy field QC methods. Can you say something what we have for the connectivity?
Yeah, I think for the connectivity is particularly easy with these resistor loops that we're using. I mean, I think that's always nice in the field to be able to do that last check to see that you are on par, that your sensor is working correctly, that everything is okay before you deploy, maybe for a long period of time. So these easy quality assurances that you can do here with an inductive sensor where you connect a resistor loop is very nice to do these simple checks. So this easy field quality assurance is definitely the way to go.
And I think for other sensors, we have suggest other methods. For oxygen, you just measure in the atmosphere between deployments, and you can see then how much sensors have drifted, if they have drifted, because when they drift negative, and you compare that with the air pressure. For pressure sensors, the same thing. You can log them in the atmosphere and compare with the atmospheric pressure before and after. For current sensors, we have, for example, test unit for the single point. We have methods for most of our sensors, how end users can check them and verify that they are working more or less as they should. It's not calibrations, but it's verifications.
Great. And so this is the sort of a pre-launch of this new high accuracy connectivity sensor. We have our first production batch in production right now. We already have pre-bookings for some units there, but we will be able to ship a couple more units before the end of the year, as long as this first batch is not completely booked. And so if there is anyone who has some extra budget money to spend, then please get in touch with us. We can deliver by the end of the year. We have an excellent supply department that has been able to stock components for Aanderaa all through the year and have not had significant delays in our deliveries, which we're really, really happy about. So with that, just let you know there's actually an opportunity to get one of these in your hands this year, 2021, as we're wrapping it up pretty quickly here. So with that, I've had some notes come through here and trying to organize, because there are some questions that are coming up. And I will take the first note here, which is interesting. And are you planning to do a trading campaign for the new connectivity sensor? We had not planned that, but in general, we're very much in favor of being able to trade in equipment and make sure that equipment is also that is not being used can be maybe refurbished or reused from a sustainability perspective. That is a very good thing to do. So although we don't have it planned, we will definitely take it into consideration, because I do think that's something we want to do. We do have trading programs that we are going to run for other types of sensors and other types of solutions. So this could also be an opportunity. So let's say that as we take it as a good idea. Is it planned for other interfaces than RS-232-422? Yes, it is. We're doing a project to implement Modbus on this sensor, along with turbidity sensor and also the oxygen optode for aquaculture. And these sensors would be available sometime in the first half of next year to enable bigger systems with many sensors bused on a Modbus. So although it's not part of this release, please watch out for it coming up soon. Let's see, now there's many notes here. So let's see here. I think this was already answered. How do you tell the difference between bubbles and silt? But maybe you want to say that about surrounding the turbidity sensor. You did show some data there, Anders, from your local pool. And how do you tell a difference by using acoustics and the turbidity sensor?
I mean, basically from what we know and what we have seen in field applications and also in this more controlled pool application, is that the turbidity does not react to bubbles. Mm-hmm. Then I don't know if, because that's what we see also when you have breaking waves along beach applications and so. Mm. But then when you have breaking waves, you also have a lot of resuspension of sediment, so data typically becomes noisy. Mm. So it's always a little bit difficult in that case. But then acoustics, they really get acoustics. Are very affected by bubbles. It's very strong acoustic reflections against bubbles. But yeah, what we have seen from field and some trials we have done is that the turbidity sensor does not pick up the bubbles. So it picks up the mineralogenic particles mainly, and to some extent organics, but much less.
Okay, I got a couple of questions. Two of them are more or less the same, but I will start with one here. The new connectivity sensor, is it an improvement on both firmware and hardware? And that is, yes, it is. It has both one of the hardware, both mechanical hardware and electronic hardware has been updated. On the mechanical side, it is about repositioning the temperature sensor to a much more favorable place so that it responds much more quicker. There's also improvements in the electronics and also then in the firmware driving it. So there's basically improvements in all those. But then the next question, which are two of them more or less the same, is regarding fouling. And of course, that is something we maybe should have said more about during the webinar as well. So I will take one of them here. Solving the fouling problem in coastal application is in shallow water. Is there for Aanderaa system, is there a solution coming for that? And Anders, we have a couple of things that you're using that we can recommend, and also that we are providing from Aanderaa. So why don't you say a little bit more about that with regards to UV light, for instance?
Yeah, we have a collaboration with our South Korean company, which represents us in South Korea, but they also do technical development, and they developed systems, UV light systems, which are low power hungry. Before that, UV light systems were more power hungry. So we have sensors, we have combinations of our oxygen optodes and conductivity sensors, which are built into one unit, and with UV light and conductivity and oxygen combined. And these are out in the field now for trials. And yeah, I think in the beginning of by mid next year we will have more results from these. Ocean Sensor, Ocean Tech, the South Korean company, already did a lot of field tests with our sensors and with the UV light. But and some units were integrated with oxygen. Some were just putting the UV light as a separate, like a torch, to the sensors, and they also provide such units with separate batteries and a separate unit for UV lights, and it seems to work very well. Then of course there are the classical methods with copper tape and so, but that does not work on the conductivity. Conductivity should be kept without naked metals close to it, because there are these proximity effects that you have on inductive conductivity sensors.
Great, thank you, Anders. And I hope we have answered all the questions that came in online. And if not, we will get back to you after when we send out the recording, I guess. Yes, and if we are really pleased that so many of you came and joined us today. Anders and I are very happy to be able to provide you with this information with the great help of Reidun. And you will be getting some more information, all of you registered, and that therefore you can enjoy that after you've done with this webinar. So thank you all very much for attending, and have a great day. Thanks. Bye.
Thank you. Bye-bye.